Hi, my name's Jon Wakefield, and I'm going to be giving the second lecture today on Bayesian subnational estimation using complex survey data. So the outline of this lecture is that first I'm going to motivate the use of smoothing models to alleviate problems with sparse data. Then I'll talk about Bayesian inference, which gives a mechanism by which we can impose temporal and spatial smoothing models. And finally, I'll combine those two to talk about space-time smoothing. So by way of motivation, when we see estimates over space or time, so just empirical estimates of proportions, for example, then we want to know whether the differences we see, are they real or simply reflecting sampling variability? To this end, we can formulate statistical models that look at the totality of data. So rather than just looking at data within a particular time point or in a particular area alone, we can look at all of the areas or all of the time points and then try and use the information from all of them to come up with better estimates in each of the specific areas or time points. So this is going to be particularly beneficial in sparse data situations. So what we're going to try and do is smooth over areas or time or both in order to get more reliable estimates. Another way of thinking about this is in terms of penalization. So we penalize deviations from our neighbors, whether they be spatial or temporal. And I'm going to start by talking about temporal models because those are a lot easier to think about because they're one-dimensional and they have a direction. Then we'll see how we can extend those to spatial situations. Now, as a generic indicator, I'm going to just think about the prevalence of some condition, for example, death within the first month of life. And then in this lecture, I'm going to talk about think about just simple random sampling. So we're not going to worry about any particular complex designs. So we know that the data that we get in the scenario we're most interested in, i.e. low and middle income countries, we get data from complex surveys, in particular stratified cluster designs. But we're going to think about that in the next lecture. Today we're just going to think about simple random sampling within areas or time points. So just to motivate a little further, what we see here is the three figures on the right here show simulated data with three different sample sizes. So in each of these, in the top panel, we've sampled 10 people, or let's say people in each month. So we've got 60 months worth of data here. So in the top panel, we sample 10 people. The middle panel, we sample 20, and at the bottom, we sample 200. In each of these cases, the true underlying prevalence here is 20%. And so those dots, as you can see, vary between 0 and 50%, but that's just sampling variability we're seeing. There's no temporal pattern here. All we're seeing is the sampling variability. And so in particular, in that top panel, it looks very much like there's a lot of signal. You know, we see these fluctuations between 0 and 0.5, but really they're just sampling. It's just sampling variability about this flat curve. So in this second scenario, now I have actually included a trend. So we have this quadratic-like trend, so low becoming high in the middle months, and then decreasing again in this symmetric fashion. And so again, we see a lot of sampling variability about those curves. So I've included this example because we want to see whether there's always a worry that we're going to over-smooth. So the models we're going to use are smoothing models. So we're going to use neighbors to smooth over time in this case. And we want to know, are we over-smoothing and losing all the signal? So we'll return to these examples later when I've talked about some temporal smoothing models. In the second set of examples, I want to think about the spatial case. So again, we have a binomial experiment. So now we're sampling within areas. So we have areas indexed by I. So the counts yi here are the counts of some disease, for example, or some condition in area I. We're going to do some binomial sampling where there's an underlying true prevalence of pi. And then we're going to collect different sample sizes. So the denominator of that binomial is denoted n. And so we're going to look at 50, 100, and 500 samples in each area. And again, I'm going to look at two sets of simulated data. In the first, we have the true signal is on the top left, and it's just flat. So you see the yellow colors here are high prevalences, are just around 30%. Dark purple is more like 0, so no cases, no observed cases. And so even though we've got this flat map on the top left, the samples, the one to the immediate right is just sampling 50 people from each area. And we see we're covering the full range of 0 to 30% over those areas. So it looks from that plot, if we just saw that and didn't think about sampling variation, that there's quite a lot of subnational variation in this prevalence. In the bottom left, we now have 100 samples, and we can see the ranges decrease. We're not seeing any yellows anymore. We're going to these light greens, and there's no dark purples. And then we have 500 samples. We're seeing a lot flatter empirical proportions, although there's still variation. So again, the idea is, can we use smoothing to define somehow spatially to come up with more reliable estimates in each of those three data situations? And then here is the second set of simulations where now the truth does show some subnational variation. So the top left, we do see variation, so slightly higher prevalences in the central area there. And so the question is, can we pick up that signal and sort of filter out the sampling variation to reveal the true signal? And you can see again, as we pass from 50 to 100 to 500 samples, we see the map flattening towards that true signal. So the bottom right looks a lot more like the top left than, say, the one to the top right does. Okay, so when we're thinking about, let's start thinking about how we might intuitively, how we might want to smooth. So one thing we could assume, the ultimate smoothing is to say all the prevalences are the same. So across the whole of the map or across time, we have the same prevalence. So that's kind of the ultimate level of smoothing. We just say it's flat. At the opposite end of the spectrum, we could assume that each of the prevalences, so PT in the temporal sense, are just distinct. So there's no linking between that prevalence at that time point and any other time points. So that, again, is an extreme. So we'd have 60 parameters there in that example I showed of over 60 months' worth of data. The first example, we have one. Then we have this an in-between model, which would say, OK, we expect the prevalences to be similar over time. And so the question is, how can we model similarity? And so there are many different smoothing models we could consider. The first one we could think about, a very simple one, would say there is some common, so thinking about the true underlying, we're moving towards being Bayesian here, and so we're going to assume the underlying true parameters are assigned probability distributions. So we could assume that all of the prevalences arise from some common distribution. So it's the same at every time point, and so that's going to allow fluctuations, but unrelated in time. And so I'm going to refer to that as the IID model, where that's shorthand for independent and identically distributed. So there we're going to penalize from some overall level. So as I mentioned, we can think of smoothing models as penalization, mechanisms for penalization. And so we can imagine penalizing deviations from some overall level. The second type of model we could think about would say, OK, we're going to assume that they're correlated over time. And so we're going to encourage the prevalences to be similar to their neighbors, where we're going to for some suitably defined neighbors. So there we're penalizing deviations from a local level rather than an overall global level. And just to the right here, I show a picture of, this is actually undefined mortality over provinces of Kenya. So we see those smooth curves. They were obtained using a particular form of smoothing, temporal smoothing, that I'm going to talk about shortly. And just for some notation, these models are known as hierarchical or random effects models. And whatever we call them, the key element is going to be a smoothing parameter, which we're going to have to estimate. So the level of smoothing is going to be estimated from the data. So Bayesian inference, it turns out, is it's a paradigm by which we can carry out statistical inference, and it's a very convenient way of implementing smoothing models. So the key elements of a Bayesian analysis are the sampling model, sometimes called the likelihood. That describes the distribution of the data. So we need to write down a probability distribution based on unknown parameters theta that we believe generated the data. And then at the second stage of the model, we specify a prior distribution, which expresses beliefs about the parameters of the likelihood. And that's where the prior distribution is where we're going to impose the penalization or smoothing. And so given those two elements, so we have, by Bayes' theorem, we have the posterior distribution, which is the quantity on the left here, is proportional to the likelihood times the prior. So the unknown parameters are theta there. The data is being conditioned on, so that literally what that equation says is that our beliefs about the unknown parameters theta, given the data we see y, so vertical bar stands for given. So given the data we've seen, fixing the data, we're going to, the posterior probability or density assigned to any particular value depends on how likely that value of theta is, how much it's supported by the data, and how much prior support we give. So there's the two elements combining in this simple multiplicative fashion. Sometimes informative to think of this on the log scale, so we're saying the log posterior is the log likelihood plus the log prior density, and then I've written in the more perhaps intuitive notation of, so we're combining the sampling model with the penalization. So it all looks very, very simple when you first come across Bayes' theorem. It looks as if it's all going to be easy to implement and interpret, but as ever, the devil is in the detail. So in that situation, I was really thinking about, I didn't make it explicit, but I was thinking about a univariate parameter theta. Typically, and in all the models we're going to consider, we're going to have multiple parameters, perhaps hundreds or thousands of parameters. So then that formula still holds, but now you have a probability distribution over a huge space, and so, or with large dimensionality. So we want to summarize that distribution. The way we typically do that is between one or two dimensional marginal posterior distributions. So we have a multivariate posterior distribution, and then we integrate out or average over the uncertainty in the parameters we're not interested in visualizing, and then we can just see one or two dimensional summaries. And then we can go one step further and summarize those posterior distributions. So for the univariate posterior distribution can be summarized via its posterior mean, posterior standard deviation, or more generally and more informatively, usually posterior quantiles. So for example, we could report a posterior median and an interval of, say, 90% width. So we could report the 5% and the 95% points of that distribution. That gives us what's known as a credible interval. So that's the Bayesian analog of a confidence interval. But now it's interpreted as a probability statement. So given the model, we can say there's a posterior probability that we believe the parameter lies between two particular numbers. So I won't dwell on this, but for quite a long time, like a couple of hundred years, the use of Bayesian methods was really not widespread, and part of that was philosophical, but part of it pragmatically was because the computation required was really not possible until basically the 1980s. People started to dream up techniques which allowed posterior inference to be carried out in practical situations. Now, there's many different types of summarization or computational techniques that could be used to do Bayesian inference. We're going to use one that's very convenient and fast called the integrated nested Laplace approximation, or INLAR. So this was developed by Horvath Roux and colleagues 10 years ago now. And there is a very nice R package which implements this methodology. And there's now there's a number of books have appeared on INLAR, and there's a lot of practical experience, and suffice to say it's a very reliable computational technique for the sort of models we're going to be interested in. So now here's a very, very simple example of Bayes' theorem, which is very simple and not really realistic, not useful in any particular application, but it is quite informative about how the Bayesian machinery works. So let's suppose we've got n observations, yi, from a normal distribution with unknown mean mu and known variance sigma squared. So so we've got n contributions to the likelihood there. We can summarize those simply by saying, in terms of the likelihood, that's identical. We get an identical likelihood if we say y bar given mu is normally distributed about mu with variance sigma squared over n. So we see there the square of the familiar standard error sigma over root n. Now let's suppose that our beliefs about this unknown, so we have a single unknown parameter. Let's suppose our beliefs about that unknown parameter can be expressed via a normal distribution. So this NMV is a distribution we're going to specify in advance. So those M and V are specified by whoever's analyzing the data to reflect their beliefs. So we pick two numbers there. And then what that prior distribution is doing is penalizing. We can see this in the bottom equation. So values of mu which are far from M are going to be penalized because we're squaring that distance. So we have a minus sign here. So this is the log posterior on the left-hand side here. And you see it's the combination of two sums of squares. And so because of these minus signs, we want these squares to be as small as possible. So when as mu moves further and further away from m, then we get more and more penalized, the greater the penalization. And that distance is relative to v, which is this prior standard deviation. So if we pick v to be very small, then we really, as soon as mu deviates in any great extent relative to v from m, then it's going to become very unlikely that it will gain much support in the posterior. So that's how our prior beliefs are being used in this calculation of the posterior. The data is entering through this first term, which says, okay, y bar, those values of mu are supported here that are close to y bar, the sample mean. And closeness there depends on sigma over root n. So we get these two potentially conflicting sums of squares. So we can see that on this picture here. So here, this blue curve is a normal density which reflects the prior. So it has mean 15 and variance 3 squared. And then the data, the likelihood contribution arises from this green curve. So this turns out that this arises from we're assuming there's a sample of size 10 here with sample mean 19.3. So this green curve is centered by about 19.3. And so the posterior must take into account these two pieces of information. So it does that probabilistically. And in this example, it turns out the posterior is also normally distributed. And we see this compromise between the two sources of information. The likelihood is more peaked here, so the likelihood is more influential. But we see that the posterior is moved towards the prior in relation to the likelihood. So in that example, we just had a single mean. So now we're going to think about having multiple parameters and how we can specify priors which tie those parameters together in the fashion that we'd like to impose some kind of smoothing. So thinking about temporal smoothing, if we're looking at some particular population, so let's think about a non-infectious disease where we wouldn't expect sudden spikes. If we're looking at some chronic condition, then we would expect there to be some smoothness in the prevalence over time. We wouldn't expect sudden jumps. So the first thing we might think about is to say, well, let's assume we have some linear, the model is linear in time. So our prior says we expect a linear increase or decrease over time. So that might be okay over very small periods, but that's going to be too restrictive over a longer period. The next thing we might think about is higher degree polynomials. They can produce very weird and wonderful shapes, and so that might fit the data well, but it could also be very unstable. So the trend is, well, the most common models in this sort of situation are local smoothing models. So we don't look across, so when we fit a linear model, it's taking the data from the whole of our time period and smoothing linearly. So rather than do that over the whole of the time period, now we're just going to look locally and use the information from our neighbors, however we choose to define that. So the models I'm going to talk about are random walk models, which have got, again, quite a long history in Bayesian smoothing and have been used successfully in many applications. Again, just to emphasize, the smoothing parameter is going to be crucial here, how we pick the level of the amount of penalization. So let's think of some generic parameter phi t. So phi t could be the mean of these models are going to be defined via a normal distribution. So the most practical way of applying these is to thinking of some parameter on the whole of the real line, because that's the support of a normal distribution. So we could think of the log it prevalence. Prevalence lies between 0 and 1, so it's log it, i.e. log p over 1 minus p, is defined on the whole real line. So let's think about the mean of the log it of prevalence. That's at time t, and we'll call that phi t. And so sometimes quite confusingly, different authors describe these random walk models in different ways. We can think about the complete distribution. So the aim here is to specify a prior distribution over these t unknown means. So we've got some means indexed over time, phi 1 through to phi t, capital T, and we want to specify some prior which holds them together in some way, doesn't allow them to become too wayward at any particular points. And so we could think about the joint collection of all of those phis, phi 1, so that's a t-dimensional probability distribution. Or we could think of the one-dimensional probability distribution. So in time, this is perhaps the most natural. We say, if I tell you what the mean was in the last time period, what do you now believe about it in this current time period? So that's a conditional model where it's conditional on the past. Or we could think about, so this one actually explicitly here, I'm thinking about what's called a random walk one, where we're just thinking about the only neighbor that's relevant is the immediately previous neighbor. And this can be extended, as we'll see. We could think about two previous neighbors, or we could go as far as we like. So that's a one-dimensional distribution. Another one-dimensional distribution would condition on both of the neighbors. So now, if we're not thinking about this in time, we could just think, so going in the direction of time, going forward in time, we could say, okay, here's our collection, phi 1 through phi capital T. Let's just think of a particular point, phi a small t now, somewhere in between the two endpoints. And then we could say, if I gave you the two neighbors, what would your beliefs be about that current time point? Now, the nice thing, so as I said, the most natural one to think about here is this phi t given phi t minus 1. But that doesn't extend easily to a spatial setting because we don't have a natural ordering in space. Whereas the first and the third formulations do have a natural ordering. So they're the two that I'll focus on because that'll make the jump to spatial modeling simpler. So here's the explicit form of this random walk one model. So what we're saying is that given the two neighbors, what we believe about phi t is that it's normally distributed, and the mean of that normal is the mean of the two neighbors, and then there's some variance sigma squared over 2. So sigma squared here is the smoothing parameter. So if the smoothing parameter is small, we're imposing a large amount of smoothing because we're not allowing this phi t to deviate from the mean of its neighbors. It has to stay close. If it moves too far away, that penalization is going to become too great, and so unless the data are really strongly saying that point is very aberrant from its neighbors, then we're going to be pulled into the neighbors. On the other hand, if this sigma squared turns out to be large, then that's going to be weaker smoothing because we're allowing deviations from that mean to be far greater. So the form of the density here, that joint collection, the phi t given the two neighbors, the actual form in terms of the normal. Now let's write down the density, the univariate density. So we just see now explicitly, we look at phi t minus the mean of the neighbors squared. So again, if we deviate greatly from this, we're going to receive low density. And that's what this plot here shows. So here these 6 points will be, say, the observed means for so we're at time, imagine we're at time 3 and we want to think about smoothing phi t. So that's what this mean response here is. And what this model says, I'm going to look at my immediate neighbors, take the mean of those, that's that blue dot, and then this red normal density is the different possible. So where will phi t fall here? So if phi t falls up here, it's going to this value here has got very, very low support from this smoothing prior. Whereas if we're in the middle, if phi 2 is in here, then it's encouraged. So it's being encouraged to lie close to the mean of its two neighbors. And the width of this red density is determined by sigma squared. So as I just said, the values of phi 2 that are close to the mean are favored. And that favoring is relative to this sigma squared. So the strength of the penalization depends on sigma squared. So this model is quite nice, but one property which isn't too appealing in the setting we're in is that often we might want to predict forward a few steps ahead. So phi t is the last point we observed. Suppose we want to go ahead by s steps, then we can work out the density. This model is very tractable, so we can work out the density of new observations. And it turns out that the mean of that density, so if I want to predict forward, the mean of the density is phi t, the last time point. So it's centered on the mean at the last time point, regardless of how many steps we go out. What happens with the step length is the step length does come in here, which says that the variance of our prediction is linear in the number of steps we go out. So we get this variance increasing linearly in time as we move further from the last time point. But we're going out horizontally. So that's unappealing because we're not picking up any local trends. Just the final thing on the random walk 1 model, that's the way we can express the joint density now of the t means. So basically what we've done is we've stacked together, we've taken the product of those t minus 1 terms, and so we see now that we've got this local penalization as we go through time. They're always being constrained to lie close to their neighbors. Just some notation we'll use later. So this is the same density here, but this t tilde, t dash means this tilde is read as is a neighbor of. And that's going to be useful when we get to spatial modeling. We can write that compactly in this form. So with phi, this quadratic form, phi transpose q phi, where q is this so-called precision matrix. So those of you familiar with the multivariate normal, this q is the inverse variance covariance matrix. One really appealing property of these models is that the form of this precision matrix is this very simple banded form. So we have these numbers down the diagonal and the off diagonal, then the rest of these entries are all 0. That's very, very appealing because it means the computation is very fast, because there are all sorts of numerical or linear algebra tricks that allow you to evaluate this density very quickly when you have this form, as opposed to a form which is, this is called a sparse matrix. A non-sparse matrix would have non-zero elements everywhere, and that's a pain to use. That's a pain to work with, especially when you're having to do it multiple times, which is what we're going to be doing when we fit these models. So these random walk models have this very nice sparse representation in terms of the joint density, which is the way we would, if we had to code this up, this would be the natural way to do it. So as I said, the random walk ones, were intuitively appealing, but they have this unappealing flat predictive distribution. So the next random walk up from there, the random walk 2, the way that works is to say, okay, rather than saying I'm similar to my previous phi t is similar to phi t minus 1, what we do now is we deviate, we penalize deviations from the slope. So imagine, look here, we're looking at the slope. So phi t minus 1 is looking at the slope between those 2 points. And then we're looking at the previous time slope. So phi t minus 1 minus phi t minus 2. So we've got a slope, and then we have another slope. And what we're saying is we want those to be similar. The most favored form here would be the slopes are identical. If they're identical, we get the maximum support from the prior. So if the slopes start to deviate too far, so this one would be fixed, this one's moving. If this one goes too far away, then it's going to be penalized greatly. And it's not, this model isn't saying this is impossible, it's just discouraging it. So if the data very strongly say, okay, we're suddenly going flat or suddenly becoming steeper, then that's allowed, that's not impossible, but the data are going to have to strongly tell you that because the prior is saying, actually, we think we're very close to linearity here. Going to the predictive distribution, so going s time steps ahead, so this is saying what's the mean at time t plus s. Now we pick the last value, but then we take the slope of the last 2 points. So if we've got a trend going like this, then whatever those last 2 points are doing, we're just going to follow that down. We take a hit in the variance, so the variance is now cubic in s, so now the variance is going to really balloon outwards, which is maybe a good thing anyway, because predictions going too far out in this setting is a very dangerous endeavor. Okay, and then just to show you what the form of the joint density looks like, we see these, if we rearrange this, we can kind of see this here. We get 2 phi t minus 1 terms here, so we get minus phi t minus 1 plus phi t minus 2. So that's what this term here is. So we're saying that we want this quantity to be small. So phi t plus 2 should be close to minus 2, the previous one, plus the previous one. Or, sorry, close to 2, that one minus that one. And so we can write that compactly in this form, where we have this now slightly more compacted, slightly more non-sparse matrix, because now we have elements on both the off-diagonal and the second diagonal away from the leading diagonal. But it's still sparse, so it's still going to be very fast. And just to show you how these models work in practice, this is just a generic data set, the volume of water in the Nile times some very large number. So here, this is over 100 years worth of data. These black dots here are the the observed data. Then we have 3 curves here. These are all fits from a random walk 1 model. If we have a very large smoothing parameter, then we just, this model, the limiting case is a horizontal line, which is just the mean of all the data. If we go the other way and make a very small smoothing parameter, then that's not very useful either, because that's just basically interpolating all the points. So the Goldilocks curve is this one that nicely sort of follows the general trends, but doesn't, so what we want is something that doesn't over smooth or under smooth. And so typically in applications, we'll place a prior on sigma squared, and then let the data refine that prior to give us what the data, the best amount of data for the best amount of smoothing for this particular data. That's for the random walk 1. If we look at the random walk 2, we see very similar behavior, except now, so we interpolate for small amounts of smoothing. We again interpolate the data. The limiting case now, because we've got these trends from linearity are being discouraged. So the limiting case here is just the linear model that passes through those points. And then in between, we've got this smooth curve, which hopefully will not over or under smooth. These just show you realization. So here I just simulated 20 realizations on the right, on the left rather, from a random walk 1. So we see a more jaggedy pattern. There's much more local deviations are allowed. So this might be relevant if you've got a trend where you think there could be local conditions where we do get movement away from the, we do get a more jagged pattern. Maybe a random walk 1 is more suitable, whereas the random walk 2 on the right has got these more smooth curves, these 20 different curves from the simulated from the prior. So just to summarize, the IID model, that smooths to a flat line. The random walk 1 just has local linear behavior, and then the random walk 2 has local quadratic behavior. These are all of the random walk models are examples of what are called Gaussian Markov random field models, which there's a huge literature well summarized in that book by Rue and Held. And so there are all sorts of very appealing properties that these models have. So how do we apply these for the simulated data? Well, now we're going to apply these models on the scale of the log odds. So we've got our likelihood. So our Bayesian model starts with the likelihood. So we've got denominators nt. So we take samples of size nt at each time point. Then we've got true prevalences pt. And what we say is the odds of PT have got this exponential form, which is equivalent. So this is a logistic regression model with an intercept alpha, and then deviations from that alpha, from that overall level, phi t. So these are the local trends. And we assign a random walk 2 model to those means. So these means are on the language of GLMs, these are generalized linear models, these are on the linear predictor scale. So that's where these Markov random field models are generally specified for normal random variables, so it's natural to put them on the linear predictor scale. And then we finish the model with priors on the smoothing parameter and on the intercept. And so what happens when we apply that model? So this is the case where the 3 sample sizes for a flat curve. So the red curve here is the posterior median prevalence estimate based on the data and on that random walk 2 prior. So we see, yeah, it's not following the blue curve exactly in this n equals 10 case. Here we do see a lot of low prevalences, so there was lots of 0 counts here. So the curve is pulled slightly down. And again, at the end where we see in these last, 8 or 10 months, all the data are below the curve. So yeah, it's pulled down, but we've smoothed a lot towards the blue curve. By the time we get down to samples of size 200, then we're pretty much picking up exactly the curve we'd like to pick up the true signal. And then this is the case where we have this curved pattern. And so again, we get more deviations in the small sample case because, here we do see quite a lot of data above the line. So yeah, the model can't decide here whether that's true signal or whether it should be staying close to, how close to the neighbor should it stay. So, but by the end we get to this n equals 200 case, we're really picking up the trend. So that's shown that if we're careful, we can pick up true signals. And this just shows how in a real data case, so this is actually applying this random walk 2 model to data from household survey data collected in Ecuador. And so this is actually applying the model at a 5-year. This is looking at over the whole of the country. This is taking data every 5 years and smoothing via a random walk 2 model and then doing a prediction. So this survey was around, I think, 2013. so predicting forward to the next 5-year time period. And here we actually applied the model at a yearly time scale. Again, we predict forward, and you can see the variance increasing as we move further from the last collected data point. Okay, so now we're going to look at extending these models to space. So there are overall there's two big ways that people, or two main ways that people have chosen to model spatially. So one is the discrete spatial model. So here, these are the 47 counties of Kenya. So here we have one color in each county. And so because we've applied a smoothing model which says every county has the same underlying prevalence. Whereas down here, we've got a continuous spatial field. So now we're seeing local pattern within the counties. So I'm going to talk about the pros and cons of those two models. In the summer package, which Richard has been talking about in the parallel lecture series, we fit discrete spatial models for the reasons I'll talk about shortly. Continuous spatial models, they're often based on what are called model-based geostatistical approaches. So suppose we've got point data, so we do a household survey, or we do a collection of those in a cluster, so the notation is reflecting that scenario. So YSC is the binomial count of the number of events we see for people who can be thought of as residing at location SC. So S is a two-dimensional point, so that's a latitude and longitude, if you like. And then we've got some sample size at that location, so we collect, let's say we might interview 30 people and find out how many have got that condition of interest, Y. So we've got the interest is in this prevalence, P, which is now indexed by S. So what's the prevalence that we'd like to have at this village or cluster level? So the discrete model would say, okay, that prevalence is going to be written as the X bit of alpha and intercept plus a discrete spatial variation, so some spatial smoothing model across areas, and then we've got some random shocks so that we allow some deviations from this overall spatial patterns if there's very localized events which are unrelated to areas around. And just this slightly irritating notation, so ISC basically says the area I within which cluster C resides. So this is just a function which takes a point location and says which area does it lie within. So that's a discrete spatial model. The continuous spatial model says, okay, now we're going to just say that there's a continuous spatial field. So we've got some underlying field which we add to the intercept, and then we might allow random shocks at the cluster level. So that's, from the geostatistical literature, that's known as the nugget effect. The idea being if you took a sample, then you might take a measurement and you'd hit a nugget of gold or something, and then you take another sample very, very close by and you'd miss the nugget, so you'd see huge changes, but it's really just small-scale spatial variation. That's one interpretation of the nugget. The other is just as measurement error, or measurement error. So that was for the point data. Now I suppose we've got counts. These models extend to this situation as well. We could say, okay, now I suppose we see a number of counts in an area, again with a denominator ni, so now it's just at the area level. And again, we have the same form here. The discrete spatial model is exactly the same form. The continuous spatial model is a little different because now the prevalence in area PI is the integral, so it's the average of the prevalence across the field, where that average is across the area, where that average is with respect to population density. So this ds here is population density, and so we have to average the prevalence to get the point-wise prevalence to get the average prevalence across the region. So we have to average this field, the spatial field that we saw in the previous. So in this operation here, I haven't included the nugget effect. So I've assumed that is just measurement error, so we don't want to include it in predictions. So I've just said generically, I've talked generically about discrete spatial models and continuous spatial models. Let's get concrete. And so here's again that discrete spatial model at the aggregate level, say. So here is our IID random shock in each area. More interestingly, here's a model which says, so this is the famous ICAR, intrinsic conditional autoregression model, which this So this model is known as the BYM model for Bisseg, York, and Mollier, who formulated this model in this paper in the early 90s. So this model says include two random effects, one that's IID and one that has this particular spatial structure. So what is the structure? Well, it says the unknown, so what we're saying is conditional on the neighbors. So we're going to define neighbors in some way. So maybe neighbors share a common boundary. Then we say, given those neighbors, what do I believe about the spatial field in my particular area? And so what this model says is, I think it's going to be close to the average of my neighbors. So that SI bar, that's the average of let's suppose there's MI neighbors. This is the notation I introduced earlier. It said, for all those neighbors J of I, so maybe there's 4 neighbors, so MI is 4. Let's take the average of their spatial field, of the spatial random effects in those 4 areas, and that's where we're going to center our distribution. And then we're going to have some variance sigma squared S over MI. So the more neighbors we have, the more informative this prior on the spatial field is. So this is the natural analog of the random walk 1 model. We're looking at first order neighbors, where the neighbors now are defined by sharing a common boundary, or some other definition which we might want to use. And again, we've got this smoothing parameter, which determines how strong the smoothing is over space. So if we have large values here, that indicates that we've got quite a strongly varying a spatial field which has got quite strong amplitude. Just to give you an example of what a neighborhood scheme looks like, so this is for areas in, there we go, first typo I've spotted, Oriah, so that's the prior, really. And so the spatial random effects S follow this distribution we saw before. Now here is the precision matrix. So here we've got our 6 areas, and so we can see, for example, that 5 and 6 are not neighbors, and 6 and 4 are not neighbors, so we see zeros here. These numbers here are the number of neighbors. So you can go through and just see how that precision matrix is defined. In this very simple case, there's not such a graining computation, but if we had, say, for like Nigeria, where we have 774 LGAs, then we want to have a sparse precision matrix, because inverting a 774-dimensional matrix is doable, but you don't want to do it too many times. Okay, so I'm not going to say any more about, after this slide, I don't think, about continuous spatial models. Continuous spatial models are popular with some groups, such as WorldPop and IHME, who produce a lot of maps of health and demographic indicators. But so continuous spatial models are definitely theoretically appealing, because discrete models, we have to pick some arbitrary neighborhood structure, and so there may be sensitivity to that. There's continuous spatial models. The priors can be very, very important. So you might, if you're not careful in the way you specify priors, you could over-smooth or under-smooth. Also, if we want to do area-level smoothing, which is what this course is, these sequence of lectures is all about, we start by saying we want to come up with estimates, say, at the admin 2 level. So we need to be doing some kind of averaging. So this is the averaging we saw earlier. So we have to pick a population density surface. And those, in the context we're interested in, those are not particularly reliable, and they change very quickly over time. And so we would rather avoid that step if we could, and the discrete models allow us to do that, at least in their simplest forms. Okay, this just shows a comparison of various approaches. This is actually looking at secondary education prevalence for women aged 20 to 29 in Kenya from the 2014 DHS. And so I won't talk too much about most of these plots. This is for those that are interested. These are the direct estimates, so weighted estimates. These are doing some sort of smoothing of those estimates, so I'll talk about that in my next lecture. But these are the BYM estimates of prevalence levels. So here, red areas have got lower educational attainment. Blue areas have higher educational attainment levels, so blue is preferred here. And then this is using a continuous spatial model. So you can see that actually we get very, very similar. If you look closely, then you'll see, this is white, and this is got a slightly higher estimate than this area here. But overall, they're very, very similar. So these top plots are point estimates. These bottom ones are widths of credible and confidence intervals. And we see now there are more differences. So there's still ongoing work to how we can calibrate, in particular, these continuous spatial models. The calibration can depend very strongly on the priors, which is another reason we're choosing to go with the discrete models. So now let's go back to those simulated data sets. So here we've got in area I, remember we just had these counts with a sample size ni, and we had different sample sizes. So again, we're going to do the modeling on the linear predictor scale. So the log odds of the prevalence are linear there's an intercept, and then we have this spatial random effect, and then these IID shocks. We're going to assume ICAR model for the spatial random effects. So we do have a BYM model here. I'm not going to talk about prior choice here. It's a big topic, but suffice to say that there are reliable priors we can pick now in most scenarios for this model. So in this paper, there's a lot of discussion of this model, and under these priors, which are very nice and are implemented in INLAR, are called penalized complexity priors. Okay, so here's the first scenario. This is the flat risk case. So here's the observed data when we have 50 samples in each area. So again, we see this lots of subnational variation. Once we apply the BYM model, we assume this effectively that we recover the true surface. This is for n equals 100. So what we see in these three pictures is that this middle plot gets better as we get more and more data. But even here with 500 samples, we've still got sampling variation is evident, even though the truth is, flat. And so the BYM model is doing what it should do. So now the question is, well, is it over smoothing? Should we, do we worry we're going to lose all the highs and lows, which of course is the lows in particular are the places we're interested in if we're in a mortality setting. So here's n equals 50 when we have this as the truth. And we can see, we are doing a little, maybe we are over smoothing slightly in some places, but overall, we're losing all these very high areas, and these light greens are, again, much too high. So this model is not providing a good representation of here, whereas here we're getting closer. But we only have a sample of size 50, so maybe the prior is influencing more than we'd like here. So here we've got n equals 100, and so now we see that we are getting far closer to the truth. And by n equals 500, it's difficult to distinguish between the left and the right. There are small differences, but looks like we're covering the true surface. Okay, and this just shows in a real example. So this is the difficult admin 2 problem of where we have data from a Nigerian DHS. We're looking at vaccination rates here, and these white areas, they had no samples. This model, the way this works in a Bayesian setting, if you've got no samples in an area, you can put in the unknown prevalence in those areas as an unknown random variable, and then that is effectively imputed using the neighborhood structure. So here we see this map, which, and there's quite a lot of smoothness. You can see smoothness here. We do collections of greens, which are high vaccination rates in the south of Nigeria, or relatively high. And we can see now that this is where that smoothing is coming from. So we're smoothing over these white areas and filling them in with what the model believes are the best guesses given the neighbors. Okay, so now let's move to space-time smoothing. So a quick digression into factor models. So suppose we've got two factors, A and B, with capital I and capital J levels. And so let's think what models we would, if we had a continuous response, what are plausible models for this? How would the response vary, the mean response vary with these two levels of the factor? So the first model we might think of is this main effects only model, where we have an intercept, and then we have deviations from that intercept, which depend on the rows and the columns only. So here we have no interaction terms, nothing indexed by I and J. So eta I here is the effect of being at level I for factor A, regardless of whatever the level of factor B is. So we don't care where we are with respect to B. So J can be anything. Being in row I, if you like, always has the same association. So the movement away from alpha is always the same, regardless of what value J is taking. So there's no interaction. So now we can add in an interaction term. And so now delta ij is interpreted as the additional effect beyond eta I plus phi j. So that says the main effects would say this, and now we've got some deviation from that, which allows the data to deviate from this very simple main effects model only. So let's think about those delta ij's. What would we think they would be like? Well, what sort of model would we specify them? So if we're a Bayesian, we want to put a prior on these parameters. So if these factors A and B are just some nominal things like color or gender or something which has got no natural ordering, then we might be content to put a prior on which doesn't relate levels to each other, levels going across the levels of the factors to each other. But now let's think we're in the case of having something like space or time. Then we would expect some kind of smoothness. So if I represents space here and J represents time, then we might expect smoothness over space and time, and we might expect the interactions to be smooth as well. So here is a space-time model in this binomial setting. So we see our usual model now. We've combined the models from the previous two sections. So we've said we've got some overall intercept. We've got our IID term, a noise term in space. We've got a spatially smooth term, a discrete spatial random effect. We've got some IID in time, so one-off shocks, so they could be due to natural disasters or war or something of that kind just occurring across the whole of the region in 1 year. And then we've got smooth terms, which have got we have some smoothly varying parameters. So this is a main effects only model where we don't actually have any interaction between space and time. And here I could say that the smooth spatial terms are ICAR and the smooth temporal terms are random walks. So that's often going to be not very realistic, particularly if we look over long periods. That model would say that if an area starts off high in terms of, say, infant mortality, it'll stay high for it will stay the same in the relative, so we can imagine a set of parallel curves. So they might all be going down, that's the temporal trend, and there may be spatial differences between them, but that ordering isn't changing. So that's usually going to be quite unrealistic. So we'd like to, now just denoting by theta IT, the linear predictor, so on the x-bit scale, we'd like to allow for more flexibility in that main effects model. So then the question is, so now we put structure on these quantities, what structure are we going to put on the delta ITs? So there was a paper by Norheld in 2000 which looked at 4 different types of interactions. One that just says they're independent, that's the type 1 interaction. So the interactions just don't depend on anything that's happening around it in space or time. Type 2 interactions have got temporal patterns, but nothing in space. Type 3 interactions have got spatial smoothness. So that we look at what's happening within a year, we can say, okay, my interactions are going to be similar to the interactions next to me via some definition of neighbors. But across time, we get a new set. Every time period, we get a new set of interactions. There's no smoothness across time. So these 2 and 3 aren't really that appealing, whereas the type 4 interaction says, now we're going to have temporal trends in the interaction terms which depend on both space and time. So if the interactions around me in space are high, so if I'm deviating from the local pattern, from the main effects rather, they're all saying the same thing. I'm going to be pulled up with those. And if the previous time period, they were also high, then they're going to be moved towards those as well. So this is really the most appealing in a prevalence mapping context because we would expect smoothness. And for what it's worth, this is what the form of the joint density looks like. But you can see the random walk 2 structure. This is for a random walk 2 model. So here we see this is the form we saw earlier, but now extended to cover both space and time. So this is saying, what we're basically, intuitive, what it's saying is we have these slopes, and the slope is close to the slopes of the neighbors and also for neighboring time periods. So both neighbors in space and time, we can look at their slopes, saying if we knew the temporal trends in the interaction and the spatial trends and the trends in neighboring areas, then we want to look similar to those. And these models are all implemented are in line within the summer package. So here this just shows how these models work for 8 different provinces of Kenya. So we see this is applying that model to, so these dots here are direct or weighted estimates. So we have weighted estimates, and then these black curves are the solid curves or after we've applied a space-time smoothing model. And then this just shows over between years 85 and 2019, so predicting the end. So we have these light greens are very high levels, so up to 20, so 200 deaths per 1,000 live births. And then it's dropping. So we see here, this area seems to be high over the whole period. So maybe there's some evidence here of less interactions, at least for that area. But then we see as we go through time, we're getting to these darker colours and lower prevalences of under 5 mortality. And this just actually looks at the space-time interaction terms. So we can see they're quite different. So this is showing these random walk 2 crossed with ICAR. That's the model here. That's the type 4 model we're using. And we see that, yeah, we're seeing these are the interactions. So these are the deviations from the overall. We have a spatial map, and then a main effect. So there's a particular map, and then we have a particular temporal trend. And so we can imagine imposing those two together to get these maps over time, which are, in general, they're dropping. But this shows that, relatively speaking, in the central area, relative to the overall time trend, the central area is doing worse progressively over time. Whereas, this one here, the northeastern region, is doing relatively better. That's dropping relative to the overall. There's a sharper decline relative to the overall trend. So we see they're quite different, and they're smooth as we expect, because that's what the model has used. Okay, so just finally, as I've said, there's lots of experience using these discrete spatial models, so they're very appealing in that respect. And the computation is also very, very fast. Continuous spatial models, that's still an area of a lot of research, and so in the future I expect they'll become more popular. But at the moment, we've chosen not to package those up within the summer package because they're very difficult to automate. There are all sorts of things I didn't talk about, like how the computations are carried out. So for large data sets, all continuous spatial models make some sort of approximation. So in the implementation which many people use, which is known as SPDE, that requires specification of a mesh. So you effectively discretize space with a very fine triangulation mesh. And so there's lots of issues in doing that. It's very difficult to automate that. And then we have these other thorny issues of prior distributions and how we do the aggregations with respect to population density. So in this lecture, we've just talked all about space and space-time models for simple. Some of the examples I showed were for surveys, but I didn't talk about how the details of how we fitted those. So in the next lecture, I'm going to talk about how we apply these models to complex survey data. Then here's just for those who are interested, here are some books on Bayesian spatial modeling. And then finally, I'd just like to thank the Hewlett Foundation and IUSSP for providing funding for this series, and also my colleagues, Richard and Sam, who I've had long-standing collaborations with them, and as with the other lectures, many of the materials you can find at this particular website. Okay, thank you.